This is the first lesson of Unit 9, which deals with the gas laws. We're going to start out talking about this kinetic molecular theory. So just looking at this name, kinetic, you've probably heard of kinetic energy, right? So that's the energy of motion, things moving. And so this is just a theory about how molecules move. First thing you need to be aware of is that particles in a gas are considered to be small hard spheres with an insignificant volume. That means they've got a lot of space between them, which means we have the ability to compress them or move them closer together. You can't do that with solids or liquids. They're already as tightly packed as they can get. Second part says the motion of particles in a gas is rapid, constant, and random. So what that means is they're just moving around, bouncing off the walls, bouncing off each other. They're just moving randomly, kind of in a straight line until they hit something and they ricochet off and go in some new direction. The third part says all collisions between particles in a gas are perfectly elastic. So what that means is that they just bounce off one another. Okay, the particles aren't really speeding up or slowing down. Okay, like pool balls, you hit pool balls and they bounce around, but there's like friction and they slow down. With these, they're just bouncing off one another and the energy is conserved. Okay, what you need to be aware of though is that this idea of pressure is the result of simultaneous collisions of gas particles, either with each other or with the walls of their container. So it's as they're pushing out on these things, they exert pressure, this force. Let's see. And so our atmosphere exerts pressure. Okay, so you've heard of atmospheric pressure. Well, what causes this? Well, basically, what it is, it's just all of the gas particles. It's just a column of air sitting on top of you, pushing down on you. And so you can measure this with a device called a barometer. So this is the earliest form of the barometer. Okay, this was made by a Italian scientist named Evangelista Torricelli. And basically what it involves, you can see he had like an open dish of mercury here, then he put an inverted glass tube called a eudiometric tube. And basically what he did is he filled this tube to the brim with mercury and he inverted it in there. And then the level of mercury dropped. And up above here he had a vacuum, so just a space void of matter. And what he noticed is that this level would change, would go up and down. Okay, and so what was causing this was just the weight of the air, the weight of the atmosphere pushing down. Okay, so as you have the air pushing down on top of this, if it's pushing more, it pushes more mercury up the tube. If it's, less pressure, then the mercury drops. And you can measure this. Let's see, so that's basically barometer and barometric pressure. These are some different units of pressure. Okay, so we have millimeters of mercury. If you've ever been to like the doctor's office, they take your blood pressure. That's usually the unit they measure it in is millimeters of mercury, and it's exactly what it sounds like. It's just how high of a column of mercury could support above like a dish. So how many millimeters up this tube it would go. So that's a common pressure unit. Torr is another one. You'll notice torr is the same as a millimeter of mercury. That was named in honor of Torricelli. This next one, atmosphere, that's a common one. So 1 atmosphere of pressure is equal to 760 millimeters of mercury or 760 torr. There's this other one called kilopascals. And so an atmosphere is the same as 101.3 kilopascals. And then last one, PSI. This is probably one you're familiar with because this is like if you're going to inflate a basketball or a bicycle tire or whatever, it'll say how many PSI, how many pounds per square inch, so how much force that exerts. So these are all units of pressure. There's this thing called standard temperature and pressure, or it's abbreviated STP. Standard temperature and pressure is 0 Celsius or 273 Kelvin. And so Kelvin is the temperature scale that we have to use in the gas laws. We'll get more into that later when we talk more about specific gas laws, but just be aware Kelvin is a temperature scale and it's based on absolute zero. We'll talk about absolute zero later, but just be aware if you need to convert to Kelvin temperature, what you do is you take whatever the temperature is in Celsius, and you add 273 to it. And that'll give you your Kelvin temperature. So 0 Celsius, 0 plus 273, so 0 Celsius is 273 Kelvin. Okay. Notice that it's not a degree symbol, it's just Kelvin. All right. And pressure units, we already talked about some of these. 1 atmosphere, 101.3 kilopascals, 760 millimeters of mercury. 29.12 inches of mercury. Sometimes you'll see inches. It's not real common, but you may. Or 14.7 psi. These are all constant values. I'm going to give you guys a sheet that has all these standard values on there. And I mean, you can just use them. It's just they're facts. All right. It's like saying one foot is 12 inches. It's the same thing. These are all standard pressures. These are all standard temperatures. Since I guess I mentioned absolute zero on the previous slide, absolute zero is basically the temperature of which motion of all particles theoretically ceases. So they stop. Because what temperature really is the measure of the average kinetic energy of particles, or basically how much these particles move. Well, if you look at like Fahrenheit or Celsius, they have temperature scales where they have things that are in the negatives, all right? So very commonly it gets into the negative Celsius temperatures because that's anything below 32 Fahrenheit out. And so in the winter, it's almost always negative Celsius. And that's based upon the freezing point of water. With absolute zero, it takes care of that. It gets rid of all the negatives. There are no negatives because it gives the 0 point, this point where nothing's moving. All right, no particles are in motion, and there can't be less motion than no motion, and so that's why it's called absolute zero. It's the absolute lowest temperature. And like we said, Kelvin, a degree Kelvin is the exact same size as a degree Celsius. So to convert, all you have to do is take Celsius plus 273, or I guess vice versa. We're not going to deal with Dalton's partial laws of pressure, so we're not going to do that. We'll get more into Avogadro stuff tomorrow. Or it might be Monday, actually. We're talking about like molar volumes of a gas. But this is the guy, Amadeo Avogadro. So you guys remember Avogadro's number. 6.02 times 10 to the 23rd is 1 mole. He actually didn't come up with that number. Okay, he didn't know what a mole was. He was a scientist. He dealt with gases, and what he stated was that if you had the same volume of gases at the same temperature and same pressure, they have equal numbers of particles. So this would be atoms, molecules, whatever. So it's related to the mole, but it's not the mole, and he definitely didn't come up with that number. It was named in honor of him. So as we kind of mentioned before, some of these properties of gases, the first thing we have to understand, gases are compressible. We can push them together. We can force those atoms or molecules closer to one another because there are spaces in between. And so, like we said, they're generally far apart. Applying pressure moves them together. We can compress them. You may have an air compressor, right, at home, which takes air and smashes it together and increases the pressure. We're going to be looking at this chapter. There are basically 4 variables that will describe and will affect different properties of a gas. And so we're going to look at pressure, temperature, volume, and then number of moles. So if we know these 4 things, we can tell a lot about different gases. I'm going to show you some Phet simulation stuff showing you the relationship between some of these things. But these are the general gas laws, and we'll get more in depth with these, again tomorrow. But gas laws, pressure and volume, they're an indirect relationship. It means one goes up, one goes down. Pressure and temperature, they are directly proportionate, or they have a direct relationship, meaning one increases, so does the other. Same thing with temperature and volume. They are also directly related. One goes up, the other one goes up, and vice versa. Probably the easiest way for me to demonstrate this is to demonstrate it using Phet simulation. So give me just 1 second here, and I'll get this up so we can look at it. All right, so this is a little Phet simulation dealing with gas laws. And so what you'll notice here is I have a container that is a vacuum. It has no particles in here. Okay, it is void of matter. And so what you notice right off the bat, no particles. Notice there is no pressure because there's nothing pushing on the container walls. Likewise, there's no temperature because there isn't anything moving around. So what we're going to do is we're going to add some particles to it, and we're going to see how we can kind of change some of these things. So let's see here, I'm going to take it, I'm going to just pump some particles in here, all right? And so you'll notice these particles are kind of moving around, they're colliding with the walls. As they do so, okay, notice it's affecting the pressure. Notice that it affected the temperature, so there is motion, and then as they collide with the thermometer, they impart their energy to it, and the temperature went up, okay? So we can do a number of things here. I can show you um, how volume will affect it. Okay, so let's say this is a magic box. I can change its size. Okay, so let's say I'm going to grab this, I'm going to pull it in. All right, I'm going to make the volume smaller. So you'll notice that the volume is getting smaller. Notice the pressure is going up, the temperature is going up. And this makes sense because both of these things really relate to collisions of the particles, with each other and the walls of their container. Well, if they're in a smaller confined space, they're going to collide more frequently. Okay, so volume goes smaller, both temperature and pressure go up. Okay, let's do the other one. So if we make the box bigger, if I take this and I expand the box, the container, okay, notice they're spreading out. Okay, they don't collide with the walls as frequently. Okay, you'll notice that the pressure is definitely dropping and the temp dropped, I think, a little bit. Okay, so expanding gases, volume gets bigger, pressure goes down, temperature goes down. Here, let's say I'm going to add, let's look at like temperature. Okay, let's say I'm going to heat it up. I'm going to put some flames on it. Notice the particles are moving a little bit faster. They're speeding up. Temperature is rising. Pressure is increasing. Okay. If I put ice cubes on it and cool it down, remove some of the energy, you'll notice the pressure is going down, the temperature goes down. Okay, let's leave it here. Let's say I add particles. I add some particles here with the pump. As I'm adding particles, every time I pump some particles in there, the pressure increases. So does the temp. If I want that to go down, if I open this door on the top and some of these particles escape, you see them escaping out here to the universe, the pressure's dropping, temperature's going down. Okay. And so those are just some of the things you can kind of sit here and manipulate. I can probably share a link, and if you guys want to play around with it, it's kind of a fun simulation just to kind of see what happens. And if I keep going, keep adding pressure and pressure, it's building, building, building inside here. Eventually, you blow the lid off and all those particles escape. Pressure drops, temperature drops. But just some kind of neat thing just to kind of play with. All right, we'll probably stop here, and then tomorrow we'll actually get into some of the gas laws and we can do some math calculations with these things.